The acoustic properties of materials and structures are described in terms of reflection, absorption, and transmission. For the interior of a space, reflection and absorption are generally considered. Transmission is included in absorption, and the loss of sound energy that no longer returns to the space is not considered. For the outside of the space, the transmission of sound energy through the enclosure is usually considered. The acoustic properties of materials and structures are related to the frequency and angle of incident sound waves. The same material and structure will produce different reflection, absorption, and transmission for sound waves of different frequencies. Sound waves of the same frequency will also produce different reflections, absorption, and transmission when incident at different angles. Therefore, the acoustic properties of materials and structures need to correspond to certain frequencies and angles of incidence. Any kind of material and structure will reflect, absorb, and transmit incident sound waves. The proportions of the three are different. The proportions vary with frequency and incident angle, and the valuation indicators of the three characteristics are also different. Therefore, materials and structures are determined on the one hand according to the characteristics with a relatively large proportion, as sound absorption, sound insulation, or reflection, and on the other hand according to the function that is mainly considered during use. Sound-absorbing materials and structures are widely used to solve acoustic problems in places with high sound quality requirements, and used to control noise in general buildings. The physical quantity that characterizes the sound absorption capacity of materials and structures is the sound absorption coefficient. The sound absorption coefficient is between 0 and 1. The larger the value, the greater the sound absorption capacity. According to the different incident angles, it is divided into vertical incident sound absorption coefficient, oblique incident sound absorption coefficient, and random incident sound absorption coefficient. The random incident sound absorption coefficient is also called the diffuse incident sound absorption coefficient. The normal incident sound absorption coefficient was measured by the standing wave tube measured. The random incident sound absorption coefficient was determined by the reverberation chamber measured. There are few cases of vertical incidence and oblique incidence in the architectural acoustic environment, and random incidence is common. Usually, the arithmetic mean of sound absorption coefficients of 6 frequencies of 125, 250, 500, 1000, 2000, and 4000 Hz is used to represent the frequency characteristics of materials and structures. The arithmetic mean of the sound absorption coefficients of the 4 frequencies of 250, 500, 1000, and 2000 Hz is sometimes used. The latter is also known as the noise reduction coefficient. The average sound absorption coefficient is equal to the total sound absorption of the room divided by the total room interface area, since it is difficult to determine the area of people and objects in the sound field. The sound absorption of a single person and object is often used without the sound absorption coefficient. Next, let's do an exercise. The dimensions and sound absorption coefficient of a room are listed in the table. Find the total sound absorption and the average sound absorption coefficient at 500 Hz. The amount of sound absorption is equal to the sound absorption area multiplied by the sound absorption coefficient. Since the sound absorption coefficient and the area of the floor, wall, and ceiling of the room are not equal, the sound absorption is calculated separately and then summed, which is 8.1 square meter. The average sound absorption coefficient at 500 Hz is equal to the total sound absorption of the room divided by the total internal surface area, which is 0.086. Sound-absorbing materials can be roughly divided into 5 categories according to the appearance and structural characteristics of the material. Porous materials are suitable for emanating medium and high frequencies. Plate-like materials are suitable for emanating low frequencies. Membrane material is suitable for emanating low and medium frequencies. Perforated plates and flexible materials are suitable for illuminating medium frequencies. These materials can be used alone or in combination. The porous material combined with the air layer can improve the low-frequency absorption capacity. The combination of perforated plate, porous material, and air layer can improve the absorption capacity of its frequency band. The combination of the membrane material and the air layer can improve the low-frequency absorption ability. The salt absorption principle of porous salt-absorbing materials is that when salt waves enter the interior of the material along the macros, the air in the voids vibrates. Due to the viscous resistance of the air, the friction between the air and the hole, and the heat conduction, part of the salt energy is converted into heat energy and lost. It can be seen from this that only materials with holes open to the outside, interconnected with each other, and deep inside the material have the ability to absorb salt. The surface of the finger A is rough with peace, but no macros are formed, so it is not a porous material. Finger B has macros, which are interconnected and deep, so they belong to porous materials. Finger C has macros, but they are not connected to each other, so they are not porous materials, but can be used as thermal insulation materials. Finger D has macros and interconnected, so it belongs to porous materials. The main factors affecting the salt absorption characteristics of porous materials are airflow resistance, porosity, apparent density, structure factor, material thickness, surface treatment, installation conditions, and environmental conditions. The most important of these is airflow resistance, which reflects the resistance of air to pass through a porous material. The flow resistance of a material per unit thickness is called the specific flow resistance. When the thickness of the material is not large, the larger the specific flow resistance, the smaller the air penetration, and the lower the salt absorption performance. However, if the specific flow resistance is too small, the salt energy lost due to friction and viscosity will be reduced, and the salt absorption performance will also be reduced. Therefore, there is an optimum airflow resistance for the porous material. Porosity refers to the ratio of the volume of connected pores in a material to the total volume of the material. The actual determination of airflow resistance and porosity is difficult and can be easily controlled by apparent density. The larger the apparent density, the smaller the porosity, and the larger the specific flow resistance. It can be seen from the figure on the left side. With the increase of thickness, the salt absorption coefficient of the medium and low frequencies increase significantly. The high frequency does not change much, and the total salt absorption increase. It can be seen from the figure on the right side. If the thickness is unchanged and the density is increased, the salt absorption coefficient of the medium and low frequency can also be improved, but the flow resistance will be increased. It can be seen that the density also has an optimal value, but the effect is not as good as increasing the thickness. In the case of the same material, when the thickness is not limited, the porous material is better to be loose, but when the thickness increases to a certain extent, the improvement of the salt absorption performance is no longer obvious. The same material can be stacked and used in the order of increasing density to increasing the salt absorption coefficient. It can be seen from this figure that the salt absorption coefficient increases with the increase of the thickness of the air layer, and the effect is no longer obvious when it also increases to a certain value. In actual use, the porous material needs to be surface treated to avoid scattering of the material into the air. The cover material is required to have good air permeability to avoid affecting the salt absorption characteristics. Use metal mass, fiberglass cloths, and other covers that have little effect on salt absorption characteristics. However, when the perforated plate is used, the high-frequency salt absorption coefficient will be slightly reduced, and the low-frequency salt absorption coefficient will be slightly higher. When the membrane is used, the salt absorption coefficient of the medium frequency will be slightly higher. It shows that the perforated plate and the membrane are combined with porous material to form a composite salt-absorbing structure. The surface of the formed set can be decorated, but care should be taken to avoid the water-based paint from closing the pores, and it is not suitable to use paint. Think about it. Can the centrifugal glass wall board and rock wall in thermal insulation materials be used as porous salt-absorbing materials? Does it have the function of heat preservation and salt absorption at the same time? What effect does the plaster layer outside the insulation material have on the salt absorption performance of the insulation material?